In this video, we are going to start a new topic of functions. Now, the introduction to this, some of it is revision, and some of it will just take a wee bit further than we did in National 5. We're also going to look at domain and range. So firstly, a wee bit of revision. A function is a rule which connects one set of numbers to another. We can express a function in the following forms. So we can either have a table of values, we could have a graph, we could have an arrow diagram, or we can have a formula. So in National 5, generally speaking, when we had functions, specific functions topic that we used formulas in, but we also saw function notation within our graph work as well, where we might have had a table of values and we would have had the graph. So you have seen a few of these before. Now the notation, just a reminder, f bracket x bracket, and we say that f of x, so it's a function in terms of x. Or we might have, for instance, g of u, so function g in terms of u. And we can call our function anything, and then we can express our function in terms of whatever variable we want as well. So that definition that we had for functions, let's make that a bit better, a bit more accurate. So a function is a relation between two sets where each member of the first set is related to only one member of the second set. So let's really look at what we actually mean by that. So here we've got some points. I've given you 5 points here. And I suppose what we notice about these points is that the x values, there's the graph firstly, you'll notice that each of the x values are unique. So each of those values only occur once. And they all have a different y value. So you can see that 4, 12 is connected, 0.5, 15, etc. So they're all different. So that makes that a function. If we now look at this one here, so we've got a set of points again. So we've got 412, 415, 518, 521, 624. Now if we just plot that graph firstly, you can see that there's a lot of similarities between the points in here and here. But you might notice firstly that the 4 occurs for the x value twice. But it maps to 2 different y values. And you'll notice that the same thing happens with the 5. So we have the 5 twice for our x values, but 2 different y values for that. And that's what makes that not a function. Let's look at another example. We've got a table of values here, and you can see that we have unique x values. Have a look at the graph. Now you might notice that there are 2 y values that are the same. But that's okay. They come from different x values, that's fine. And that is a function because we've got these unique x values as such. Now if we look at a similar table, and what you might notice this time is that we have 2 x values which are both -2, and they both correspond to different y values. So if we look at the graph, it looks something like that. If we look at where that -2 is, here's -2 here, and we've got 6 here, and we've got 20 up here. Now we can also see there's actually another value in here, 6 point something, and there are other places here where there are 2 y values for corresponding x values. If we take x equals 6 here, when we go up, here's 1 point, here's the other point, and that is not a function. Have a look at another example this time in the form of an arrow diagram. So on the left hand side are our x values as such, we'll call them x just now, and on the right hand side we've got our y values. So this is the first set, this is the second set. And we've got all of our members of the first set here, and they all map to only one member of the second set. So you can see here all the values are only going to one member. The x values as such are unique. So that makes that a function. If we then look at this arrow diagram, again there's some similarities here. Okay, but if we actually look at the 5 here, so we've got a member of the first set and it maps to 2 different members of the second set. So that means that that's not a function. So while these values are unique, this one is actually occurring twice as such, because it's mapping to these 2 different values. Let's have a look at another one. Now this is a function here. You might have seen this before. It's a parabola, y equals x squared, and it is a function because if we take any x value, so in this case that's probably around -3, you can see that there's only one corresponding y value for that, all the way up to infinity. If we take another x value, probably about 5.5, and there is only one corresponding y value, so that's why that's a function. Now let's have a look at this. It seems similar to a parabola, but it's been rotated by 90 degrees clockwise. And if we have a look at this one as well, we've got a circle there. Now these are not functions, and why that is, if we take for instance on the first one x equals 15, you can see that for that one x value, 15, we have 2 corresponding y values. For the circle, if we take this x value here, probably at about -6, and you can see that we have 2 corresponding y values for that as well. So those are not functions because there are 2 y values for an x value. Now obviously on these I could have picked other values right along apart from 0 here, and the same here apart from this end point here as such, and this one here. Every other value within this would give me 2 corresponding y values. So those are not functions. So hopefully now you've got a good understanding of what is and isn't a function. So we're now going to look at the domain of a function. So we're firstly going to look at some graphs, and we'll see if we can work out what we mean by the domain of a function. So we've been given this function f of x is equal to 3 over x. So let's have a look at the graph of 3 over x. So maybe slightly unusual for you, you might not have seen a graph like this before, but that's okay. Now the thing that I notice straight away about the graph, I suppose nothing's happening in this quadrant and this quadrant here, but what I also notice is the graph ever going to hit the y-axis, and is it ever going to hit the x-axis? So that's quite interesting. And what we should notice here is that it's never going to hit the y-axis, and that has the line x equals 0. So it's never going to take the value x equals 0, so x cannot be equal to 0. Now we'll have a look at another example and then we'll talk about why this is. So here's an example here, f of x is equal to 2 over 10 minus x. Now if we have a look at that graph, it has some similar features to the first one, and you might notice again it's never going to hit the x-axis. It does hit the y-axis this time. What you might notice, if I put in the line x equals 10, is it going to hit that? And the answer is no, because these are asymptotes. Now, we've spoken about asymptotes before when we've talked about the graph of the tangent function. So the graph gets very close to that line, x equals 10, but it will never hit it. And same here, it gets very close to the line x equals 10, but it never hits it. So that means in this case, x can't be equal to 10. So let's take a further look at this. So the domain of a function, and we're going to firstly look at division by 0. So remember, we can't actually divide any number by 0. If we put that into our calculator, if you put 5 divided by 0, for instance, into your calculator, it'll come up with a math error. So since we cannot divide any number by 0, then the domains of functions involving fractions must exclude numbers which would result in a denominator of 0. So if we look back to the examples we've already looked at, the first one was f of x is equal to 3 over x. So that denominator can't be equal to 0, i.e. x is not equal to 0. Now that is the domain of the function, x is not equal to 0. But to write that formally, we can say x is a real number such that x is not equal to 0. Now if we look at the second example here, we had f of x equals 2 over 10 minus x. So remember, we cannot divide by 0, so that means the denominator can't be equal to 0, which means 10 minus x is not equal to 0. And if I solve that in equation, then we have x not equal to 10. And if we write that more formally, then we get x is a real number such that x is not equal to 10. We'll have a look at another example that we've not looked at yet. So we've got f of x is equal to 2x plus 1 all over x squared minus 4x. So remember, it's a fraction, we can't divide by 0. So x squared minus 4x is not equal to 0. Now in order to solve that, we will need to factorise. So remember, we've got different types of factorising, but this one is, there's a common factor here, and the common factor is x. So it's x bracket x minus 4 is not equal to 0, and that means that x is not equal to 0, and x minus 4 is not equal to 0. So just taking each of these separately, and then our final answer there, x is not equal to 0 and x is not equal to 4. So we've solved that now. And writing that more formally, x is a real number such that x is not equal to 0 and x is not equal to 4. So at this point, I would pause the video and copy this down into your notes jotters. Now, hopefully you've had a chance to copy those examples down, and we'll just move on and look at another few examples on the domain of a function. So this first one, f of x equals the square root of x. So before I show you the graph, I want you to think about what you already know about square roots. So if you put a square root of a positive number into your calculator, you'll get an answer out. If you put the square root of 0 into your calculator, you'll get an answer out. But if you put the square root of a negative number into your calculator, it will come up math error, because you can't take the square root of a negative. So if we just look at the graph, that reinforces this idea. So remember, you can take the square root of a positive number, so that's why there is, the graph actually happens on the right hand side of the y-axis. You can take the square root of 0, that's 0, so there's a point 0, 0 there, but you can't take the square root of a negative number. So you'll notice there's nothing happening on the left hand side of the y-axis because you can't take the square root of a negative. So we can see here the domain is to do with the x values, remember, so there's no x values on the left hand side of the y-axis that are useful to us here. So that means all of the x values in the domain of this function must be greater than or equal to 0. So we have to exclude all of these values that are negative. We're only wanting the ones that will actually give us a result as such. Now let's look at another one. So this time we'll get f of x is equal to the square root of x minus 4. So remember, whatever you're taking the square root of must be equal to 0 or positive. So in this case, we've got this graph, f of x equals the square root of x minus 4. You can see the graph almost starts at x equals 4 and then will go on to positive infinity there. So firstly you can see that there are no x values in this function less than 4 because the graph, there's none of the graph occurs here, none of the curve. And all of the values are either greater than or equal to 4. So let's maybe look, just continuing on with that, at even roots. So since we cannot evaluate an even root of a negative number, so that's a square root, a fourth root, a sixth root, etc., we can't evaluate those of a negative number, and we've already talked about that, then the domain of functions involving even roots must exclude numbers which would result in negative numbers under the root. So we'll have a look at the examples that we've already done, and then we can have a look at some others as well. So f of x is equal to the square root of x. Remember, x is underneath the square root, and x then has to be positive or equal to 0. So x is greater than or equal to 0. And to write that formally in the domain, x is a real number such that x is greater than or equal to 0. Secondly, f of x is equal to the square root of x minus 4. Well, we know whatever is underneath the square root has to be greater than or equal to 0. So x minus 4 is greater than or equal to 0. If we add a 4 to both sides here, we will solve that for x, so x is greater than or equal to 4. And writing that formally, x is a real number such that x is greater than or equal to 4. And one last one, f of x is equal to 2x plus 1 all over the square root of x minus 4. Now, we've got two things going on here. We've got the square root, but we've also got a fraction. So the square root of x minus 4 is similar to this one. It tells us that x minus 4 has to be greater than or equal to 0. But remember, if it's equal to 0, that would be in the denominator. And we can't divide by 0. So x minus 4 has to be positive, it has to be greater than 0 in this case because of the fraction. So x is greater than 4, strictly greater than 4. So x is a real number such that x is strictly greater than 4. So at this point I would pause the video and copy these examples down in your notes jotter. Okay, welcome back. So we're now going to look at the range of a function. So the range of a function is the spread of possible y values. So for the domain we've been looking at the x values, but this time we're going to be looking at the y values for the range. So if we relook at this graph, you can see that this lies between 12 and 24 on the y-axis. The minimum value is 12 and it's equal to that as well, and the maximum value is 24. So y lies between 12 and 24. This time a different graph, and it lies between 4 down here. It's the minimum value and the maximum value is 20. This one here, we've got the graph of y equals x squared, or f of x equals x squared. And this time we can see that the y values, there aren't any negative y values, and it starts at 0 and it goes all the way up to positive infinity. So y is greater than or equal to 0. And for this graph here, that looks like the graph of y equals the square root of x, which we've already seen this graph as well. And again, we can see on the y-axis, the graph starts at 0 and it starts to increase, and it will keep increasing up to infinity. So y is greater than or equal to 0 here as well. So let's have a look at some examples. So the first one we'll look at is f of x equals cos x. So the range of y values here is its f of x lies between -1 and 1. So that's the final answer, but we'll just justify why that's the case. So here's the graph of y equals cos x lying between 0 and 360 degrees. And you can see that the graph lies between -1 and 1. So the minimum value is -1 and the maximum value is 1. So that's why the range is what it is. Next one, we've got f of x equals x squared plus 4. Now, I'm going to tell you that f of x is greater than or equal to 4, and this is why. So here's the graph of y equals x squared plus 4. So we've got the graph of y equals x squared would be sitting here. We're adding 4 on it, it's got that vertical shift there. So you can see that the graph starts at y equals 4 and it goes up. It will continue going up. So it lies between 4 and infinity. So basically it's going to be greater than or equal to 4. Next one that we've already looked at, f of x is equal to the square root of x. So again, we'll just look at that in more detail here. You can see it starts at 0 and it will keep increasing up to positive infinity. So f of x is greater than or equal to 0. Now, similar to the previous one, we've got f of x is equal to the square root of x minus 2. So remember that minus 2 denotes a vertical shift downwards. So we're subtracting 2. So you can see the graph looks like this. So the y values start at -2, and again they'll go all the way up to infinity. So the range of values for that graph is f of x is greater than or equal to -2. And one final one, f of x is equal to x cubed. So this time we've got a cubic function. And you can see that that's the graph of y equals x cubed. And it comes all the way up from -infinity on the y-axis. It goes all the way up to positive infinity. So f of x lies between -infinity and positive infinity. So just now, if you can take these examples down in your notes jotter before the screen goes blank.